Okay, just to confirm what we're up to then, I'll just sit down, I think. So you have this sort of sense here of, don't worry about it, don't worry about what it says. Oh, man. Oh, sorry. Okay, so you have this sense here of 2 points and a gradient in between them, like so. I use 2, 4 there, but I can just use, oh, sorry, I'm changing the wrong thing. Zoom out. There we go. So there's our points 3, 9 coming up. Pop, pop. There we go. So there's 3, 9, and 1, 1. We've got a line connecting those two, and therefore we can talk about an average rate of change between those 2 points. And all I asked you to do a moment ago was to simply extend that line. Do you know what you call it when there's a definite start and end to a line? Yeah, line segment. Whereas this is a line. And the very definition of a line is that it doesn't end. It has no beginning and no ending. So there we go. So how about I just try and update the notes that I did yesterday as we go along. So what did you get as an equation? Archie had y equals 4x minus 3. Anyone else have that? Archie, how'd you go about it, mate? Would you be prepared to actually do it on this? You get to touch the iPad instead, or is that what you bet? Yes, the magic whiteboard. Okay, so Archie is going to show us how he worked out that the equation is y equals 4x minus 3. Let's see if you did it the same way. And you're allowed to just lean on the screen, by the way. You don't have to treat it carefully. Yeah, so from yesterday, I'm just making sure it's on. Yeah. So from last lesson, we know that the gradient was 4. We worked that out, right? Click on the draw tool at the top. Okay, so from last lesson, we can start off with knowing that. The gradient was equal to 4. Oh, no, he's going to work it out anyway. Cool. Yep, that's the gradient. What x? Ethnicity. Okay, just pause there for a second. That's great. So what he's done, of course, is he's taken the general form of the equation, which is y equals mx plus c, and he's substituted in the known point. Thank you. Okay. So therefore c is minus 3. Yeah. Thank you. Good. So Archie used a guess and check method, but nevertheless, a slightly more algebraic way would get you to the same point. Good. So therefore, y equals 4x minus 3. And if I go back to Desmos, if I just scroll down, hopefully we'll see, yeah, it's cutting through minus c. So remember, the value of c is also the y-intercept. Great. So basically, what we could say is that the equation y equals mx plus c, the linear equation, because it has a constant gradient, can approximate, what's wrong? Can approximate the curve over that particular place. Is that okay? Yep. Okay. So have a look at what happens when I move those 2 points together again. Remember what I said, that when we move the 2 points closer and closer together, it approximates the curve even better between those 2 points. So as I move this down, look at the blue line. See how the blue line is now bending across? And you can sort of see that it's getting closer and closer to the curve itself. And it's sort of starting to lean along the curve. Once I get down here even more, it's not even possible to see it, but you can sort of see, if I just get rid of those points, actually, maybe just for the time being. Yeah, and the labels. You can sort of see it's now nicely placed against the curve there, right? But it has a gradient. And because it's got a gradient, we can work out, sorry, it's a line, and a line has a gradient, and therefore we can say this gradient approximates the curve, or it's an average gradient for that part of the curve. In this case, it's between 1 and 1.55. And I can bring it down, 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 and it's balancing even more beautifully on that curve there. Again, if I zoom up, Richard. Still looks pretty good, but if I zoom up even more, I can see a gap now. Now I've got a nasty gap. So there's definitely still a gap between the actual line and the gradient, and the curve itself. But nevertheless, it's pretty fine-tuning work here. So there's the curve. So we could say between between 1 and 1.15, we're getting really, really close to having a gradient that's the same as the curve. And if I keep on going down and down and down, I'll go zoom out so you can see what's happening here. We've got this line going down and down and down and down and down, 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 really close. So that's the 0.1 and 1.01. Can you see how I've got the points happening here? I've got x0 and f of x0, right? So that means I've said x0 is 1. F of x0 would be the y coordinate when x0 is 1. In other words, it's f of 1, and 1 squared is 1, so it's 1, right? Yeah, okay. If I changed x0, ooh, that's exciting. If I change x0, that'd be 3.5, and f of 3.5, which would be whatever 3.5 squared is, etc. So I hope that kind of makes sense. Okay, so f x0 and f of x0. And then the second point is this one. That's the first point. The second point, which is really close to it now, is x0 plus h. So I've just added whatever h is onto it. Does that kind of make sense? So it's the second coordinate just means a little bit beyond x0, a little bit beyond 1. Does that make sense? Okay, and you can see, so therefore what I'm inputting into the function is x0 plus h. Does that kind of make sense? So I might just do this on the whiteboard, so excuse the videos, but if it was sort of like the point 1, then because y equals x squared, then I'd be saying y equals 1 squared, and so the output is going to be 1 as well. So it's 1 comma 1. But that's basically x0, and that's f of x0. Okay. Now the other point that I've got is 1, and in this case 1.01. Okay, so that's it's not. Say that again. It's the point 1.01. That's the x coordinate. So that's the first coordinate plus a little bit. And then this next coordinate, I can't be bothered working out what it is exactly, but it's going to be 1.01 squared is going to be the y coordinate, because that's how the function is defined. Yep. No, can you see how I've subscripted the 0? So it is just a notation to say it's a specific x point. You've seen this before, right, Ambrosia? Can you tell me what the gradient formula is? Yeah. Yeah, normally put the 2's first, but it actually makes no difference at all. So you're used to this subscript notation. This means the x1, y1 is 1 point, and the x2, y2 is another point. So all I'm doing is I'm saying 0 for a base point. Like 0 is often the base level, right? Where I'm launching from. So I've just used x0 rather than x1 or x2. Is that okay? Right. Okay, yeah. Which would obviously be x to the power of 0 like that. Okay. Normally, I actually say the word sub to make it really clear. X sub 0. The subscript simply denotes different variables. Why do we use subscripts? You know it from our sequences and series work, I think, because if we just use different letters for different variables, then we'll often run out of variables, right? So by using subscript, I can talk about x sub 0, x sub 1, x sub 99, etc. I'm not limited so much then. Okay, so moving back, you can see that my second point then, which was 1.01, is just x sub 0, the first point, plus h, whatever the value of h is. In the case, you can see here on the screen that h is 0.01. Yeah? So that's why I get 1.01. It's just the first point plus h, plus a little bit. And the square of it is going to be the y coordinate, x sub 0 plus h squared, which is basically put into the function x sub 0 plus h. This is actually really critical thinking. So let me know if you're not too sure about anything here. By critical, I mean super important to the next step. Speak now, forever hold your peace. Because now I've used function notation, right? The function is given by squaring the input. So the input is x sub 0 plus h, and the output is x sub 0 plus h squared. Input is x sub 0 plus h. The output is x sub 0 plus h all squared. Yep. Thank you for asking. You need to ask. Anyone else? We okay? We okay, everyone? Okay. Moving on. That's going to be so confusing for anyone who's watching the video back. So I'm glad you're all here because hopefully it'll just be a reminder. So there's that point next to each other. I'll take those. Oh, and I'll leave those points up. I reckon I'm going to go through it again on the air sketching anyway. Not that I don't doubt your mad editing skills. Okay, so again, the line starts out here and it starts getting closer and closer to the curve itself. When I get down to 0.01, it's really close to the curve, but when I get to 0, the line has disappeared. Why has the line disappeared? There's only one point now, isn't there? Because h is 0. So if you look at the whiteboard work over there, we have nothing else. Also, have a look at this. Let's have a look at the gradient at that point. Oh, come on. Oh, thank you. Let's have a look at the gradient at that point. Archie was able to tell us the gradient, and we looked at it on the left-hand side of the board, but the gradient is effectively y1 minus y2 over x1 minus x2. Okay, Archie substituted in the points here to get 4. Let's have a look at it in terms of the coordinates that I've been working with. So what does x1, y1 look like? Well, I used x0 as my starting point, and then my y coordinate was just f of x0. Okay? Now, x0, yep. The 0 is essentially the same thing as the 1. Yes, it will do. I'll get to that, I promise. But before we move on, and this will hopefully simplify matters a little bit for people who are getting a bit confused with the subscripting notation, really, the x0 is just a point that I picked because it was a nice, easy point, right? 1, 1. In fact, I thought it was easy, but then there is that confusion that x sub 0 is the same as x to the power of 0, and that was confusing, right? If I'd said x sub 0 is 2, then it wouldn't have been as confusing, right? But the point is that it's just the point that I chose, right? There's nothing, it's arbitrary. So what I'm going to do is I've got to remove the sub-zero notation. So what I'm saying here is that I'm just picking any point on the curve, right? So that's what x stands for, any x coordinate of the curve, which means that f of x is the corresponding y coordinate. Am I making sense? Yes? Okay. So that's x1, y1. What about x2, y2? Well, that's that point that's a little bit further on. So I've taken my random point and I've added a little bit onto it. Okay? So that would be x plus h. And therefore, the y coordinate is going to be taking x plus h as its input and applying it to the function f. In other words, in our quadratic, it'll be x plus h all squared. Okay, so x is staying the same, and I'm just adding a little bit to it, to h. Good? 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 Okay, so what does that mean for the gradient then? We know, I'm going to flip it around this time. We know the gradient is y2 minus y1, that's the rise, over the run, which is x2 minus x1, which is the change in x. Change in y over change in x. We know that's the gradient formula from probably grade 9 mathematics onwards. So let's substitute the coordinates we just figured out. y2 minus y1, well, y2 is f of x plus h. y1 is f of x. Please note that this notation means that it's whatever value is got when I substitute x plus h into the equation. And that f of x means whatever value y is when I substitute x into the equation. Okay, you can't multiply out the f's or anything like that. It's function notation to say I'm inputting the bit inside the brackets and applying it to the function that was defined. Okay? Yes, yes, yes. Let's have a look at the bottom. I'll put it in brackets to start with. We've got x2 minus x1. But let's simplify this a little. We've got these two functions at the top, which we can't do anything about. We can't simplify that. But on the bottom, the x and the x are going to cancel each other out, and we're simply left with h on the bottom. Okay, so algebraically speaking, when I let h equal 0, what happens to that denominator? Becomes 0. And we know that anything divided by 0 is undefined. Okay, it's undefined at h equals 0. In other words, we can never work out a gradient when h equals 0, which only corresponds to the stuff that we were talking about yesterday about rates of change. And that is, if there is no difference between one point and another, how on earth do we talk about an instantaneous rate of change? And you can see that in that gradient there, that if it was only a single point, then h would be 0. And if h is equal to 0, then the gradient is not defined. Good so far? What did we do in our function study when we had a function where x was in the denominator? No, we didn't do that. No, we didn't put x into the numerator. Stop there. I think we're going too far south. What we did is we treated the particular value of x that would make the denominator equal to 0 as an asymptote. It's a value that the function reached, but never, it's a value that the function approached, but never actually reached. Now, this ties back to what we said yesterday. Do you remember yesterday I talked about limit theory? And remember how I talked about 0.9 recurring? Because it goes to infinity, it is equal to 1. It's not approximately equal to 1, it is equal to 1. We're going to use the same idea here, in that what we're going to say is that although we cannot let h equal 0, we can define the instantaneous gradient of a function as the limit as h approaches 0 of the change in y over the change in x. And you remember we saw that the change in x is just going to be h. And what we can do is, although we cannot set h equal to 0 currently, because that would give us a division by 0, what we can do is we can consider what that gradient is doing as h approaches 0. And if we can consider what's happening as h approaches 0, we can say the value that it approaches must be the gradient of the function at that point. Now, this is called the fundamental, oops, there's no umlaut or whatever that thing above it was, the fundamental theorem of calculus. Remember how I stopped calling it x0 and just started calling it x and saying it's any old value of x that we wish to talk about? Therefore, this is like a function, right? It's got a variable x, and so the gradient will change depending on what value of x that I give it, right? So it acts like a function. So therefore, we call this is called the gradient function. Okay, it's the gradient function. The notation is like this. So I'm going to talk about quadratics in a moment to explain what we're talking about. But can you understand that because I've used very general terminology here, this could work for a cubic, it could work for e to the power of x, it could work for sine x. This concept would work for any function, right? Not just a quadratic. The quadratic is just the simplest non-trivial one to use. Simplest, non-trivial means it's not just a linear equation or something really basic. F of x, so the gradient function of f of x is given by, oh, does that look familiar? I hope that wasn't a no I just heard. F dash of x is equal to the limit of h as h approaches 0 of f of x plus f of x plus h minus f of x all over h. That is the link. The reason why we say f of x and f dash of x is because the f dash of x complements the graph, which is sometimes why it's called f complement of x. It complements the graph in that its direct relationship with f of x is that when you work out f dash of x, you are working out the gradient function. It is linked to the f of x like that. It defines the gradient at any given point. Does that make sense? So f dash of 3, so f dash, it's just a new function, but it's linked to f of x. It is the gradient function of f of x, and it is linked by that. It means that f dash of 3, so if I input 3 and work out what f dash of 3 is, the output is the gradient of the function, the instantaneous rate of change when x equals 3. If I input 3 into the gradient function, it means that the value I get out of the gradient function, whatever that happens to be, would be the gradient of f of x when x equals 3. So to go back to Desmos, yeah, yes, I won't stop though, sorry, Sophie. So if I look at Desmos, if I get rid of all of the sort of extraneous data here and just have the line like so, as close as I can get using Desmos, this is basically the gradient of this line is the gradient of the point when x equals 1. Don't worry about the subscript 0, just imagine that's x. So as I moved x up to 3, say, for example, you can see the gradient has changed, right? It's steeper. And so if I went f dash of x, f dash of 3, beg your pardon, I would be working out the gradient of this line. And f dash of 4 would be the gradient of this line. And f dash of a half would be that line there, and so on. So you can see quite nicely that we have this sort of like, what are you typing up, Jeremy? I'll go through that. Yeah, that's the next step. Zoe and Jeremy, is this? I feel like this is not maths work you're doing. This is intellectually the stuff you need to be across, because I can teach you just how to do it like a robot in 5 minutes. Okay. So that's what we're seeing here. Now, the linking concept I haven't covered yet is that this line here that takes on the same gradient as the function does across these values is called a tangential line. It's a tangent. And the tangent simply means the straight line that touches the graph at a particular point and has the same gradient. And you can see why it would have the same gradient, because it's basically the average rate of change, except at a particular specific point. Yep. It has an infinitely changing gradient. It's not really, Ansel, because you're talking. I know what you're trying to say, and there is a sense of truth there, but because a straight line is infinite in every direction, yeah, you can say, so it doesn't quite link like you're saying, but I understand where you're coming from, and your basic premise that series of straight lines almost bounds that curve, it's like a boundary for that curve, is true. Okay, so let's take f of x equals x squared. Okay, I want to know the gradient of a particular point on that function. So the first thing I do is I work out the gradient function. So I work out what f dash of x equals, and I know that the f dash of x is the limit as h approaches 0 of x plus h minus f of x all over h. Now, on the surface, that looks like an impossible problem, right? Because as soon as I set h equal to 0, it's gone. It's undefined. I haven't finished, so hold on. In its natural form, all functions aren't able to be solved in this way. But have a look at what happens when I actually look at the function. This is getting back to your question before, Ambrosia. So here I have f of x plus h. Remember, Dijkstra, the domain, the input is the value here, and the output is when I apply it to the function. The function is x squared. So when I input x plus h, I replace the output x with what I'm now inputting, which is x plus h. So it's x plus h squared minus, and then f of x, I'm simply putting x in, and so we've got x squared again here. For some reason, so you're not alone if this is you, a lot of people find it really difficult to understand. If that's you, let me know now so I can explain it in a different way. Great. So, would you agree? I haven't finished yet though. I haven't finished, but do you understand so far? And I saw a couple of raised hands, so I'm going to move on. Would you agree that the fact that I define this in terms of x's is arbitrary? That I could, if I want, let's say it was time instead, I could say f of t is equal to t squared. Yeah? I'll get to it. There's only one h that's squared, and that's here. Oh, can I just reassure people at this stage? Can I just reassure people at this stage that I have not finished? That is not the answer there. Okay, what this is the step where I've gone from, this is what I'm asking you to understand, that if this is the gradient function here, then this translates to this, and this translates to this. Okay, that's all I'm asking you to consider right now. I don't mind if you don't get that, but don't think that this is the answer. It's not. But there's no point going on if you don't get how I could go from here to here. The only thing I've done wrong, and I will always do this, it's not laziness, it's just forgetfulness, is that every single line needs to have h approaching 0 like I've got there. Okay, so the function is just this equals this squared. To extract it a bit more, I can use INP for input. What am I doing to the input? I'm squaring the input. So when I have f of x plus h, I'm not inputting x anymore. I'm inputting x plus h. The output is going to be the square of x plus h, which is why I've got x plus h squared here. On the right-hand side, I'm just inputting good old plain vanilla x. That is the input. The output is input squared. So the input is x, the output is x squared. The input is x plus h, the output is x plus h squared. Nope, any function. Input. So the rule, which we tend to use just as x, the rule simply links an input value with an output rule, if you like. Okay, so remember, Dijkstroid, the domain is all possible input values. That's why the I stands for inputs, and we tend to call that the x coords. R is the range. It's all possible output values. We tend to write them as y coordinates. Yep. Yes. For any function for the gradient. So Ambrosia asked a question which makes me just want to go back to the function graph again. Again, using this as an example function, I could change this. In fact, I will change it. I could change this to x cubed, right? Which looks like that. No, I won't actually. I won't do that. I'll just do that. Okay, that's the x cubed graph. X is a point. X is a point, which I might just make a little bit more negative down here. And what we're doing is we're saying that to get a gradient, I need 2 points. No. Okay, I'll go back again. One more step. No. This is important, right? X is a point. H is a value I'm adding on to that point. Okay? So if X is -3, H is H is 2. So the second point, I'm putting to my own screen here, the second point is going to be -3 plus 2. So the second point is going to be -1. Just looking at the x coordinate only. There's -1. There's x equals -3. There's x equals -1. The difference is h.
Oh, okay, just the difference.
Okay, it's the value I add on to the first point to get my second point. Yep. Yes, it's not a point. It's a value I add on to the first point to get my second point. I'm going to go back to a square. I just did that to describe. The problem is that, as you can see, the gradient is quite steep, so it's difficult to sort of see what's going on. So let me go back to this. What's wrong, Sophie? You sound frustrated. So here is my first point. x equals 1, h equals 2, so my second point is at x equals 3. And we can sort of see that there's 3 there, and up we go to 3 here. Okay? We can see for my coordinates that if I am increasing the x coordinate by h, that means my input value is increased by h, and therefore my output would be f of x plus h. That's my y coordinate for my second point. So getting back to air sketch, what I'm saying here, looking at that gradient formula up here, is that I'm saying, oh, I'll go back one more step again, I suppose. Here, I'm just using my standard gradient formula. This is one y coordinate, and I'm taking away another y coordinate, and I'm taking the equivalent x coordinate and taking away the equivalent x coordinate here. This leaves me with h on the bottom, and it leaves me with f of x plus h minus f of x on the top through simplification. I can't set h. If I set h equal to 0, then these 2 points would be the same, and that would give me an instantaneous rate of change. But when I set h equal to 0, I get a denominator of 0. So therefore, it's undefined when h is equal to 0. However, if we introduce limit notation, then we can have a look at the behavior of the gradient, the way it's shaping up to be when h approaches 0. Okay, are we all on board now? Yep. I'm more than happy to go over that multiple times because it really is something that people really do struggle with. Are we focusing still? Fully? Thank you. Thank you. Okay, so moving on then, what we have here in our example is we've gone from general ideas about functions over here to a specific function, f of x equals x squared. That means the inputs are x and x plus h, and the output will be the square of the input. So if the input is x plus h, the output is x plus h squared. If the input is simply x, then the output is simply x squared. Good so far? Awesome. Okay. We still can't evaluate the gradient in any meaningful way because if I set h equal to 0 now, if I slide h all the way to 0, I've got a denominator of 0. It hasn't helped us out. So I've run out of pages, so it's going to be in big. It's going to look big from now on without my little slides. So let me just write that again. I just wish there was more focusing what I'm trying to do. I'm struggling. I'm battling illness, and I'm trying to get you to focus. We've got x plus h all squared minus x squared all over h, like so. So we do the only thing we can do to try and simplify this, and that is to expand and see what happens. So when I expand the x plus h squared, I hope what I'm about to do is second nature to you by now. I square the first term, it's twice the product in the middle, and then I square the second term. Exactly. Which equals, see this? X squared minus x squared. It's gone. What I'm left with is 2xh plus h squared all over h. And then I'm going to simplify this by taking out a common factor of h. There might be more common factors I can take out, but I'm only interested in h. Now, the reason why I do that is because once I have a common factor of h out, I can cancel down by h because I haven't set h equal to 0 yet, because I'm only interested in behavior. Okay, once I've cancelled out the h, then I'm left with the limit as h approaches 0 of 2x plus h. Please note how I've used limit h approaches 0 every single line. Once I've removed my denominator, that's when I can set h equal to 0. So now I'm sliding it down to 0, and the only thing it affects is that little h term at the bottom, right? Sorry, on the right, which means that f dash of x is equal to 2x. What you did last week was this. If f of x equals ax to the power of n, then f dash of x is equal to nax to the power of n minus 1. Have a look at what has been just worked out here. If f of x equals x squared, f dash of x is equal to 2x. The difference being you've now converted from mathemagic to understanding, which is why I didn't want you to be typing up for a different subject at the same time, okay? Because that link is critical. It stops you from being a robot and starts allowing you to get the link. F dash of x is a gradient function for the reasons we've gone through before. Limit theory will always work to find out that gradient function. However, it has been an observation in the past, as in by mathematicians, great mathematicians, that when it's applied to a power function, the result of the power function is consistently the same thing, and that is that. Okay? But it can all be done from limit theory. So going back to the start, I think, no, I don't have it here, but going back to the start, we talked about the big idea. We talked about the fact that we can take real world data and we can create a function from it. If we create a function from our real world data, then one of the important things to look at is rate of change at any given point in that data. In order to get a rate of change at any given point, we need to be able to work with calculating a rate of change at any given point. We saw that an average rate of change approximated that, but didn't really tell the full story. Remember the trip to Launceston. So therefore, working out an instantaneous rate of change not only allows us for our speedometers to work in our cars, but it allows us to interrogate any function and work out what the gradient is at any given point. And remember, those functions are often models of real world data. What we do in practice is that we learn a whole bunch of rules like the power rule so that we can take any function and therefore manipulate it. This is just one rule amongst tens and tens of rules that are used to work out functions. However, what happens if you come across a function that there hasn't been a magic rule created for? You go back to limit theory and you work it out. Okay? It's long work, it's hard work, but you can do it. What we're not interested in the IB course is forcing you to jump through too many hoops, but having an appreciation for the process and knowing that it is possible to do so without a calculator or without a rule is really important. I know that time's up. I didn't realize the time. In Monday's lesson, we will be going through an exercise in your textbook, which will be you working out gradients longhand using the limit theory. It is laborious, but it does allow you to make the connections deeper and deeper. I'm going home. Goodbye. It's going up on Google Classroom, Sophie. Yeah, I just need to Google one. Thanks.